Hi everyone. So today we are going to discuss on Pdelta analysis, its phenomenon, its effect, its philosophy, and we will try to understand how Pdelta analysis or this Pdelta effect come into the picture and how it is going to impact your structure. Now, to understand that, we need to know the basics of Pdelta analysis from scratch so that we can intuitively understand its physical behavior. Now we will take a very simple example here, a simple standing cantilever. For example, this is a cantilever column here, and if this is going to be its support, and assuming that there is a load acting at the tip called P, and there is another load acting at the tip laterally called H. P load is acting vertically and H is acting laterally. So this is the loading. Okay, now L is the height. Give it a name like L. So in this case, just recall the fundamental way of solving such static problem. It appears that the moment at the base should be H times L, H times L. But in reality, if you expand this structural behavior or the structural response, you would get to know that it's not exactly the moment at the base would be H times L. Now, here we are going to create another model. Uh, I'll go by this free sketch. Sorry for my bad sketch. Okay, now here that is the H load and that is the P load. Let me first write it. Okay, now in reality, if you expand that problem, you'd get to know that the load H is acting laterally at the tip, which would impart some lateral displacement or the drift at the tip of this column. We can name this as delta displacement. Now that we have expanded this problem, you could see that there is always a displacement due to this lateral action at the tip, right? Now, this delta displacement was not captured in our first scenario, but in reality, the displacement would be there at the tip. Now, this displacement has created a lever arm for this P load sitting at the tip. So the base moment this time would be like H times L plus P times delta. So let's give it a name like M dash. Now, if you compare both the situation, you could see that in the first one, the moment at the base was H times L, and this times the moment at the base has been expanded to H times L plus P times delta. So the structure is same, but the way that we got the different result is because we have visualized the problem from the structural perspective. We have expanded the structural behavior and we got to know that the actual moment at the base would be more than the one that we have solved by the conventional first order analysis. So this additional moment, we call it as a second order effect. So from here, you could see that this P times delta, which is the P delta, come into the picture. But the solution is not that straightforward, like one-step solution just shown for this demonstration. But solution is performed by set of iterations. So let's see how we can understand this solution. And from there, we will derive a very interesting relationship with the stability of the structure. Okay, now let's take another example. this time we are applying the load P exactly along the center line. Okay, but there is no horizontal load acting at the tip, so the moment at the base should be 0 because there is no lever arm and there is no horizontal displacement, there is no horizontal load. Now let's shift or let's apply this P loading at certain offset distance. Okay, so imagine that it is landing somewhere within the column but not exactly on the center line. This distance you just name it like delta 1. Okay, so what would be the moment at the base? So the moment at the base this time would be, give a name like m1, so it would be P times delta 1. Fine. So you could see that in some of the videos in YouTube or somewhere else, I have seen people are explaining that the bending happens along the direction of the application of the load. But that is not the true when someone was comparing between the buckling and bending. So this comparison was apparently very simple as it seems like, okay, the bending is along the direction of the a load and buckling is along the perpendicular to the direction of the load. But buckling and bending are both interrelated. Buckling is just a instability point, but it all arises from the bending. We'll show you in this discussion. So here you can see that our P load is acting vertically, but the moment has generated at the base. So we didn't apply any load laterally to just, generate the moment. So due to this eccentric distance, the moment at the base has been created. Now, due to this moment value at the base, there would be some displacement, right, to match this equilibrium condition. And that displacement would be, if I give some value like delta 1, would be ml square times 3ei. Okay, so the idea is if you apply some eccentric load there would be movement, but also there would be some displacement. A tip would be shifted, right? There is some displacement at the tip by the value of delta 1. Then we can just draw a new shape. Pardon me for a very bad drawing here. I'm really struggling to make the freehand sketch here. This is P, and if we calculate the distance from the center line, this time this distance let it be delta 2. Okay, and now this process is being repeated. Now again, this P is landing on the location which is having an offset distance of delta 2 from the actual center line location. That is the lever arm distance this time is delta 2. So the new moment would be generated. That would be P times delta 2. Right? Again, there would be a new displacement value. That displacement value would be like m2 L square divided by 3 EI, right? This was like M1. So this process is being repeated or iterated by the algorithm. Now, if we see this, that in every iteration, there is a new value of displacement and also the new value of this moment. And this moment is again the function of the applied load P. So if we go up to n number of iteration, then there would be a point when the difference between, say for example, this is the delta n and the delta n1. That is the nth level of iteration. Give it a name like x. At some point, this x would be close to 0. That means the difference would be diminished. Okay, initially the difference would be quite significant in the initial set of iteration, but over the time, the difference between the consecutive iteration would be very minuscule. It's close to zero or it could be negligible. And also this moment value, that is moment n minus 1. If I take like y, so at some point, if that gets close to zero, both these values close to zero, that means we have achieved some convergence point. Okay, convergence point means this is the point where the actual equilibrium state of this model would be established. Now, there is a very interesting thing. Now, if this value doesn't diminish, but it behaves in the opposite way, that means at each consecutive step, the difference is getting higher and higher, then this solution would be treated as a divergent solution. So, in the previous case, when we are assuming that the difference is reducing or it's getting close to zero at certain point of time, it's getting convergent. So we can say that it's convergent. But when the difference is this difference or x or y, if it is getting infinitely high, it's divergent. That means the solution can be achieved. Now, there is a very significant structural interpretation of this convergence and divergence. When it is converging, the solution is converging to some state of equilibrium. But when it is diverging, the solution is not achieving to some value. That means the structure is not stable. It is unstable structure because it is divergent. The solution is divergent and is going to collapse. Now, this is the point, the load P at which the solution is transferring from convergence to divergence. We call it the unstable point, or it's the point or known as the buckling point. Okay, that means after this point, your structure is going to buckle under the applied load P. So if we make a sketch out of this to understand the graph, so if I take this axis as the applied load P and this is the displacement, lateral displacement. You can mark it as a delta. Okay. So in the previous discussion on a cantilever column, we assume that the solution has converged under the load P. So converged means you will get some finite value of the response, the displacement or the moment at certain level of iteration. So if we keep on, let it be like P1. If we keep on adding the load, this value would behave like this. I'll show you the equation which follows this curve. Now, if you keep on adding the loads, like the one that we have just worked upon was a load P, or you can just mark it as P1. You have incremented that load, you have added more load on that, and the response was like this. Means in all the responses, yes, it was converging, but the displacement was getting immensely high. But at certain point of time, this displacement is no longer a finite value, it's an infinite value. That means the solution is diverging. So if we draw a line like this, roughly like this is the point called the point of instability or the buckling limit point. The value against this point, if we call it like PCR. You must have heard it before. This P load is also known as the crippling load. Means beyond that load, the structure is going to collapse. So you could see that from the Pdelta analysis, we can obtain the buckling limit point. And the general equation of this trajectory curve can be derived by solving the differential equation. If you solve the differential equation for this column by taking the eccentricity value of E, then you could find some amplification value. You can refer to the book like Timoshenko on structural analysis. So there you could see that the displacement, if I say this is the displacement called second order displacement under any load, and this is the displacement for the convention and analysis, or we call it the first order analysis. This is roughly amplified by the value of 1 over 1 minus Pu by PCR. Okay, this is the multiplying factor. This term or this expression you can derive by solving the differential equation. Okay, so this expression is governing this trajectory curve, this one. So if you go by the linear solution, you might get like this. But if you go by the nonlinear solution, because P-delta analysis is a nonlinear analysis, you will get this curve. So if we take this expression, you can see that if my applied load is very close or equal to the buckling load or the crippling load, then this term becomes 1. That means 1 minus 1 is 0. The denominator is 0. That means this entire expression would be having the infinite value. That means the response for the second order analysis, if you are taking the second order effect, it would be infinitely high. Okay, and if you have the PU load having a value of 0, means you are not applying any load here. Your first order value and the second order value are very close to each other. Not 0 exactly. If you take any value very close to 0 or somewhere like here, means when we have put a very minuscule amount of applied load, these values are very close to each other. So what we have learned from this discussion? So we learned from the discussion that bending and buckling are not a different thing. Buckling is a limit point at which the bending is just a response. The response under some applied load is getting to some divergent values, means the solution is not converging or the solution could not be obtained. And it's not necessary that bending would happen only along the direction of the load. If I say like this is a simply supported beam, that means it's not necessary that the bending would only apply along the direction of this load. Bending can also happen if we apply a load P at certain eccentric distance. Then also we have seen that the bending is exhibited. So this is how we can derive the buckling point from the second order analysis of Pdelta analysis. In the next session, we would see some advanced understanding of how to solve the Pdelta analysis by one step. We call it the KG matrix method. And this is the basis for the buckling analysis. The buckling analysis has also got two different approaches. One is the step by step, which is nothing but following this pattern like the one that we have just discussed here. And another is a straightforward, we call it the eigenvalue buckling solution. We will just create a single equation from where we can solve the buckling value problem or the eigen problem and determine the buckling factor and the buckling load. So hope you have understood this exact philosophy of this P delta analysis. And in the next session, we'll also discuss on the implementations of P-delta analysis in STAAD. We'll discuss on some important syntax and the commands. So if you have any queries, please post them in the comment section so that I can try to clarify your doubts. Okay, thank you everyone.